Hi, I'm Henry Segerman, and I'm here with Matthias Goerner, who's going to show us, what are we doing here? We're doing...
we're calling it Knotty Analog Oscilloscope Art.
Knotty Analog Oscilloscope Art. All right, so the setup is we've got an oscilloscope. Here's a camera pointed at that oscilloscope, and a whole bunch of electronics of various kinds. So what's going on here?
This is my first piece of oscilloscope art, and my idea was that I wanted to draw the first couple of knots from the knot table, at least go through first column in Wolfson's book. And so we can start with the unknot.
Which is not really part of the book, right?
Yes, but it's even though it's a trivial knot, it's so trivial it's called the unknot, it's still considered a knot. So this is the unknot, and then I can actually slowly turn this. And I actually get the trefoil knot. And
it's the second one on, or the first one on the real list, but the second one on the,
yes.
this modified version of the list, yeah?
Yeah, and then things get a bit more complicated to switch to the next knot. Figure 8,
right.
Okay.
Show us, let's see it on the Wolfson as well.
Yep.
So this is the figure. And what are these sounds that we're hearing?
That's the actually X and Y coordinate that the oscilloscope is plotting.
Got it.
So in theory, YouTube will probably compress it and it becomes unusable, but in theory you could reproduce this art at home up to the Z input.
Excellent.
Good. And then the next knot is 5-1. So that's another torus knot. Oh, there. Okay, good. There we have the sync-foil knot. Okay.
That's 5-2.
That's
right?
5-1.
Oh, 5-1. Sorry,
yes.
great. 5-2 next.
5-2 is next. Okay, I think that's a good.
That looks pretty good. Yeah.
Yeah. Okay, good. 5-2.
5-2.
And then let's finish this column. 6-1. I think that's a pretty good 6-1, huh?
All right. So that's the first column. So how much of the rest of it can you do, right? Okay, so what is Knotty Analog Oscilloscope? What are the different parts of this?
Yeah, so knot is like a knot you use to tie your shoes, except for a mathematician, you need to glue or solder the ends together to get a knot.
Made out of wire, so this one's solid, great.
And often you show knot projections where you project the knot and you somehow indicate where you have over and under crossings. Mm-hmm. When oscilloscope is this device, which you should think of as an Etch-A-Sketch driven by a voltage instead of a mechanical knob. And there's a whole subculture of people who like to draw interesting figures on their oscilloscope. And they've become very good at this, but in some sense, there's kind of a more pure art form that I was aiming for, mm-hmm. where you only use analog elements to produce the oscilloscope art, and you don't just cheat and connect to a computer.
So presumably there's some sort of, there's some formula which is producing this
exactly.
curve,
yes.
which you could just simulate on an ordinary digital computer. But then the point is that...
send it out to your sound card and record it.
Oh, I see. You go from the sound card out through that into the oscilloscope to make it do this.
Yes.
Or you could just draw it on a screen. Fine.
Yeah.
But the point here is that this is purely analog with nothing digital.
Exactly.
From the start to the end.
Well, your delivery eventually through YouTube will be digital.
Right. So I have the experience of seeing this with my eyes, but for everybody else on YouTube, you're just going to have to watch it through your phone, or your computer, which is definitely going to have some digital component to it. But for now, at least what I see here is the actual real. That doesn't look like a knot right there. You have to.
It's drifting a bit.
It's drifting a bit. Future Henry here. So future Matthias sent me by snail mail this photograph that he took of one of his knots. So he has some crazy contraption that attaches to the front of his oscilloscope that acts like one of the old Polaroid cameras. So this was made using actual film that was developed using actual chemicals. And so, of course, I have this experience of viewing this knot that was made using entirely analog methods from start to finish down to the chemicals on this piece of paper. You have a similar experience, but not quite the same. It's tainted by the digital pixels that were introduced the moment the light rays coming from this photograph hit the camera and then, you know, got converted into a digital file of some form and then got edited and then uploaded to YouTube. If you want the true analog experience, the only way you can do this is by tracking down, I guess, either me or Matthias. So I'll put at the end of this video, Matthias recorded a little video on how he made this photograph. So if you're interested in that, you can check that out. We also recorded a conversation about what analog means and what is the difference between analog and digital. So I'll put a link to that somewhere on screen, also link in the description. For now, let's go back to past Matthias and past Henry. And past Matthias is going to tell us, you know, how did he get his oscilloscope to do this? How did he make these images?
Oh.
Okay, so
here's kind of like, you know, I thought the
Step
really
zero.
easy, simple thing, right? We have this de-digitalized USB joystick.
De-digitalized.
Yeah.
So
I took out the USB circuitry and threw it out and directly wired out
I see.
potentiometers.
So this is forcing things to be analog if they're not analog already.
Yes, re-analogified, I guess.
Re-analogified.
Yeah, and now I actually, you know, I use it as my input device, and you can see that, you know, I can input a voltage, and I can then like actually draw on the scope or like move the point on the scope. And if I would do it fast enough, you know, the phosphorus would glow enough that you would see an image. Yeah.
So ultimately, if you could move your hand in the shape of the knot fast enough, then you would just get the picture of the knot on screen, and that would be it. That would be even more analog, or would that be more or less analog?
I don't know. I would use my brain. I don't know whether my brain is a digital or analog computer. I never figured that one out.
But so in the joystick, there's two wheels somehow.
There's two potentiometers for the joystick position that actually translate the mechanical movement into like a voltage, and then the scope can directly show you a voltage. So there's nothing really magic about a scope. I know it looks like an intimidating and complicated device, but you know, it's like an electrical driven Etch-A-Sketch.
Okay, so that's step zero?
That's step zero, yes.
Step zero, okay.
Get you comfortable with the scope and what it does, and then the next thing is I need to like steal this integrator from there. So I put an integrator, and now when I give speed to the joystick, like if I give input to the joystick, you see that it's actually interpreted as the speed with which to move the point.
Oh, so that's all. So integrating, it's as in the opposite of taking the derivative.
Yes.
That's what it's doing. I see. So
that is one integrator doing. I tell it like how quickly to move that point, and then it just like, you know, it computes the position given the speed I give with which to move the point.
Is it easy to say how it does that?
Yeah, so it has essentially three components. It has that operational amplifier. It has a resistor, which is converting the voltage into a current. Mm-hmm. And then on top of that, it also has a capacitor. And the capacitor is the element which actually does the integration, because the voltage across the capacitor you get by integrating the current.
I see. So it's sort of charging up. And then
it's charging up the capacitor, yeah.
That makes sense.
Should I draw the circuit diagram? So now, as like an exercise, you know, I can try with the joystick to like actually draw, you know, a circle. I'm not particularly good at it,
So the derivative of your trigonometric functions is more trigonometric functions, possibly with a plus or minus or something.
Yeah, exactly. So if I want to draw a circle, right, then what I need to do is I need to take my position and just, so if this is my position vector, I just need to actually rotate that vector by 90 degrees and input it as the velocity.
Right.
So yeah, so, and what does rotating by 90 degrees just mean? Well, the x-axis goes to the y-axis and the y-axis goes to the minus x-axis. So the circuit, so I'm using kind of like, for people not familiar with the analog computing symbols, I just, draw it like this. So if you connect kind of the output of one integrator to another integrator, and when you multiply here by -1 and y, then that
infinite loop
should draw, you're giving, you're using the output, use it as feedback, but you swap it and put in a -1 to rotate that vector by 90 degrees. And so that thing then, that should draw you a circle. It doesn't draw you there's a problem that the components aren't perfect, so it will kind of eventually spiral in and spiral out, so you need some extra circuitry to make it stable, but this will essentially draw you a circle. And
all right, let's see it.
Because I need sines and cosines so often, I decided to just make a box with it.
So there's a couple of those integrator chips inside of this thing.
Yep. The circuit I drew on the board is essentially here. And if we connect this up, then we should see a circle.
That is a circle.
And we can go to lower frequency.
Oh, beautiful.
It's a circle, right? And then you can go faster.
All right, so I think faster. I sort of understand what's going on. So the integrators are integrating each other, and with a minus sign. There's a -1 on the board, which is presumably some sort of component which just flips.
Yeah, it's like, there's a thing about that, like the integrators are typically inverting, which I kind of glossed over here. I think conceptually this is more understandable.
Is there voltage? I guess you can get negative voltage as well as positive voltage.
Oh yeah. So, yeah.
I guess the other thing is there's no input, right?
There's no input.
It's not connected to anything. So like.
Yep.
But where does, it's not connected to anything. How does it get going? How does it?
You mean this circuit?
Sure, yeah. I mean, the thing that you've drawn on the board just goes around in a loop. There's nothing.
Yeah, so I mean, as I said, there's a little bit of circuitry which starts to make it spiral out, and then once it's spiraled out enough, I mean, I think if I go, if we actually disconnect this, right? Okay, so now it will die.
And now it goes into the middle, yeah.
And
so it sort of loses through friction or something like that.
Yeah. And then eventually, if I turn it on again, you see that it actually starts to warm up and spiral out.
Right.
And then eventually there's a diode which clamps the voltage, so that it goes into some steady state.
So there's a little bit more that
There's a little bit extra circuitry to make this stable, but that's essentially the idea. So now we have the circle.
All right, you can do circles.
Yes, I can do circles. Yeah, let's get another one of these guys up. So I'm taking two sine and cosine generators, right? Mm-hmm. And I'm actually adding their signals. I think a lot of kids exactly know what shapes I will get out of it. So I'm taking the sine from this generator and add it to the sine of this generator.
Okay.
And then I'm adding the cosine of this generator and add it to the cosine of this generator. Right, and then I'm letting I guess typically it's the x-axis which is driving the cosine and the y-axis which is driven by the sine, right? So what do you think we will get out?
Well, it's going to be 2 sine and 2 cosines, which should just be a circle of radius 2.
If they have exactly the same frequency, but
Oh, but they don't. Okay, I see.
yeah,
So then it's going to be some wiggly thing, right?
yeah.
That
Let's
is a
see whether
circle that
we
is wobbling
can
around.
get something. So this guy here has a pretty high frequency. So right now we just can't.
So there's a low frequency one which is going around in a big circle, and a high frequeny one is going around in a very small circle. Okay.
Yeah. So this is a little too extreme, like with frequencies here. But I can like make this a little bit faster and slow this a little bit down.
Oh, there we go.
And then you see like spirographs.
Spirographs.
Yeah, and then I can like draw.
Or I guess
different-
Fourier series kind of things as well. Right?
Yeah.
Gosh.
This is like the case you were talking about, right?
Uh-huh.
Yeah.
So it's just, well, they're almost in sync, but not quite. So
Yeah.
when they're adding together, you get a big circle, and when
Exactly,
they're canceling
yes.
out, you get a small circle.
Yeah, but you can also draw like spirographs.
It's starting to look like a knot.
It does a bit, right?
Yeah.
So they're kind of like the knots I was showing fall into 2 different classes. One was like I showed you the circle, which is the knot.
Right. Yeah, okay. We've done that already.
Yeah. And then we got the torus knots, and for the torus knots.
So what is a torus knot?
So like imagine you have a bagel and then you draw non-intersecting lines on a bagel. That's like what a torus.
So the
knot
trefoil
is.
was
the
one.
The trefoil, the cinquefoil.
And 5-1 is the cinquefoil. Is that right?
Yes, that's
yeah.
Yeah.
So spirograph, you can do a torus knot, right?
Spirograph, not quite.
Not quite.
No.
Oh, okay.
You need a multiplication for a torus knot.
Oh, because I see. So on a torus, you have 2 radii.
Exactly.
There's the big radius for the center of the tube, and then
Yes.
the small radius for the little one. And so in order to get something that goes on a torus, you need 2 different radii, whereas this thing at the moment is just doing the 2 radii are the same.
Kind of, yeah.
Kind of?
I think, it's...
We should probably look this up, shouldn't we?
So I have rebuilt the generator for the torus knots.
Okay.
On this breadboard. We have 2 sine and cosine generators. This thing here is feeding into a multiplier. So this multiplier chips are actually very kind of expensive. They cost like $10 or so.
So hold on. So okay. So this is one sine generator.
This is a sine and this is cosine for the same wave. And when they go into these 2 chips here, which each one is a multiplier.
Okay.
And each one costs actually about $10.
Okay, so don't mess it up.
Yeah, don't mess it up. This like multiplication in the analog world is actually somewhat hard. And the way it works actually is that there's one phenomenon in transistor where you get a exponential function out of it, and then you multiply like you would do with a slide rule, except that to do it 4 quadrant you need a lot of circuitry.
Okay, so these are multiplying the sine and the cosine by what?
By something. Well, this is coming from here. It's multiplying by something which this circuit here is actually taking the sine from another generator and then shifting it up by some voltage. So you're multiplying by
an
like
addition.
Lambda plus sine or something like that.
Okay, so you're multiplying this sine, the one on the bottom, by the other sine plus some constant.
Yes.
Okay.
Yeah. And then if you look at the scope, that actually kind of looks like a cinquefoil, except we don't have the crossings yet.
That's the 5-1.
Exactly, yes.
On Walton's table, great.
Yeah.
Okay.
And so
because there's some parameterization of a torus which we'll be able to put up on the screen, right? what it is that's going on here.
And so what I'm attempting to do is now modulate the z-axis of the scope.
And the z-axis is the brightness again.
The z-axis is the brightness, exactly. And if I put this into the other cosine, then
oh wow!
Yeah, it should work.
Wait, so what did you just do?
So this is the cosine, and I'm connecting the cosine to do the brightness for the scope.
Oh, so it's just, you're just taking,
So
which cosine was this? This was the small one or the big one?
This thing here is the low frequency sine cosine. Right? That's telling you, that's going around this way, right?
In the big loop.
And in the sine, the high frequency sine, it's like modulating the radius. And when the cosine, the high frequency cosine, is modulating the brightness. So if you're like kind of if your radius is going is increasing, you become brighter, and if your radius is decreasing, you become less bright, and that's how you get these crossings.
I see. So the sine is only used for the radius of
exactly.
the circle you go around. You don't actually need the high frequency small cosine, but you're using it for the over under, and it works beautifully. It really.
Yeah.
Yeah, that's amazing.
Yeah. Yeah. So that's the torus knot.
So this is the 5-1.
Yeah.
And so you can also do the trefoil just by
I
messing
can do
with
the trefoil.
Yeah, let's do the trefoil. So there you're just slowing down the high frequency one, so that it's 3 times faster rather than 5 times faster.
Yes.
Or something like that.
Yes. Yeah, trefoil. Yes, there's the trefoil. Yeah.
All right. So again, and you can do any torus knot you want with enough fiddling.
You could any torus knot you want. Yeah.
All right. I guess it's on to the twist knots.
Yeah, the twist knots are a little harder. This is like spirographs, right? And I could play with this some more if I wanted to, but so I will actually connect this to one sine and this to the other sine, and then I get a Lissajous figure.
So this is no addition of them anymore. This is just
X is
sine and
X
Y
is
is
one,
sine.
Y is the other one, yeah.
So they're both sine, but they're off on where they are in terms of the phase and the frequency, so you get something more interesting.
Yeah. This is a very typical thing you would do with an oscilloscope, draw these Lissajous figures in order to actually see whether two things would be in phase or whether their frequency has a certain ratio to it or not.
Yeah.
And so one idea was that kind of if you kind of imagine just drawing a circle and then modulating the radius by the other signal, you would get like the torus knots. And
right.
The other idea I had was like if I take this, right, and I kind of apply polar coordinates. Imagine this, and you would wrap it around, and you would get a twist knot.
What is a twist knot?
Yeah, a twist knot is you have a clasp, and then you add some number of twists.
Got it.
Yeah, and I was thinking that like a Lissajous figure, if you apply polar coordinates and wrap it like that, you would get a twist knot.
I see. So this is almost the same as the torus, or as a torus knot with a 2 in it, right?
Yeah.
It's got these just 2 strands that are twisting around each other, but then you need to do this clasp thing at the top.
Yes.
I see.
Yeah.
Are these, so you're sort of constructing these things by these sort of like, I mean, what's the thought process? Like you're like, I've got these different kind of parameterizations of knots, and then which parameterizations can I actually achieve with the analog circuits that I have? Is that the sort of the... Yeah.
Okay, so what I want to build next is a voltage-controlled oscillator, meaning it's an oscillator whose frequency is actually determined by a voltage. Yes, this was generating a sine cosine.
And they have their own frequency, which is determined somehow.
Which is determined by,
by whatever goes in.
Yeah.
So they're linked, yeah.
I had potentiometers which would determine a constant frequency that I could change by changing potentiometer, but now I want to actually be able to change the frequency using a voltage. So what I will do is that I will actually put in a multiplier here and a multiplier here,
pi for product.
Exactly.
Product symbol, very good.
Yeah. And when I take these two, and this is now the input to the voltage controlled oscillator.
So you put a certain voltage in there,
Exactly.
and it so all it's doing is it's saying the output you get from the previous one is more or less by this amount than what you started with.
The speed by which the point is going gets like a multiply determined by an input voltage.
Why do you need both? Why do you need two of these multipliers? Like, because wouldn't it sort of loop around?
Because otherwise the it wouldn't just determine the frequency, but also would like collapse it to an ellipse.
I see. So it would only do one of them.
Yeah, so you do it in a symmetric way.
So you do it both of them, and then I think I understand.
So I've built this here. These are the two integrators. These are the two multipliers, and then there's a bit circuit over here, and this is the ignore this for the moment,
okay.
because that was for the later stages of the project, and I haven't removed it yet. And now, when I move the joystick, you see actually that now I can actually kind of determine the frequency with which I'm
you're going
circling about.
So the joystick is changing a voltage, which you're then feeding into that other input.
Exactly.
Which then allows you to change the frequency at which the sine and cosine are sort of going.
Yes.
Okay.
And so my idea was like, if I draw this, if I apply a sine, if I move the joystick back and forth, then I can actually kind of plot, the skeleton of a twist knot.
I see. So it's got this little. You're making the clasp go at the top, and you're reversing speed whenever you need to keep. You need to keep turning around when you reach the top of the circle.
Yes.
Got it.
The other thing about voltage controlled oscillators is that they're like at the center of all analog synthesizers.
Oh,
yes.
Musical synthesizers.
Exactly. Right. So if I make this go into like a much higher frequency. Okay, this might be loud. I didn't put any.
Okay. That is quite loud. Okay. Yes.
It's a voltage controlled oscillator.
All right. There we go. That's sort of voltage controlled. I see the obvious applications in electronic music. So there was a sine and cosine on this breadboard.
Yes.
The same sort of thing that's in this box, but just in a less modular
now we can
version.
we can first do it with audible frequencies, and then let's see what we hear.
Ooh.
Should I turn down the volume?
Yeah, I like that idea. Oh my gosh.
Okay.
Oh, wow. This is getting very Star Trek original series now.
So yeah, we definitely have a voltage controlled oscillator in
Okay,
case you didn't
good.
believe me. Yeah, and then and then if we connect this voltage controlled oscillator, so this is kind of the skeleton for
the twist knot.
That's the kind of skeleton for a twist knot. Yeah, the circuits that stabilize the circle are like kind of kicking in too strongly when I operate at a slow frequency.
I see it going back and forward.
Yeah, I think this is like kind of like now I need to get the rotational component reset. And then you kind of see the idea But if you take this and when you multiply it with the thing I just fried.
I thought we were going to cut that out.
Okay,
well, here we go.
If you take this as kind of a skeleton and you multiply it, and then you put the Z section in to make the over.
So the twisting is the twisting that you would do at the bottom of this is sort of similar to the torus knot case, except it's just that the position you are on the main part of the torus, you're going back and forth rather than just going around in a circle, and then that gets over. Okay, I mean that makes sense.
Yeah.
So and we got the footage from before of it actually working. So we're all good. We'll put that up on screen, and it'll be beautiful. How much work will it be to make that thing again?
Not too much. I think it's probably the two op-amps which are fried. I didn't fry any multipliers, which I'm happy about.
Okay, good.
I'm using a camera especially made for oscilloscopes. Before I focus the camera, I'm setting the magnification and making the aperture as large as possible. To focus the camera, I'm improvising with parchment paper since the focus plate that is supposed to come with the camera was apparently lost. Now that I've focused the camera, I'm setting the actual shutter speed and aperture for the photo. Honestly, I'm guessing here and I'm doing some test runs to see what it feels about right. One problem is that the camera takes pack film and Polaroid has stopped manufacturing pack film years ago. So I had to order some film from a company in Austria that is hand assembling the pack film cartridges. Here I am unpacking the film and inserting it into the camera. Pulling the dark tab, which was until now protecting the film from exposure, and now the camera is ready to take a picture. I'm swinging back for some final adjustments and then for a moment of truth. Say cheese. To process the picture, I need to pull the processing tab. The processing tab forces the film through two rollers in the camera that spread the developing chemicals across the film, and after waiting for 3 minutes, I can finally peel it apart to see the result.